对，无缘无故的。等会儿啊，我换了个电脑。我想想，不是电脑的问题啊，换电脑也不行。 Hello, Avia.
Hi, how are you?
Yeah, good. Maybe we need 1 or 2 minutes to manage this computer problem. Because
No problem.
we have a bunch of, many students are offline in the room to attend your seminar.
I see.
你可以进去吗？很快吗？我这网络还没连上。
Can I share my screen or not yet?
Yeah, you can share.
It says I'm not authorized.
Oh, you cannot share your screen?
It says host disabled participant screen sharing.
这个屏幕共享没有给它权限。
是那个 screen， 把主持人权限给你。
我不是 String G。
Oh, maybe now I can. Do you see my screen?
Yes.
Okay, let me just switch to full screen. And do you see my pointer?
Yes.
Okay. Good. And when I flip, it's working?
Yes.
Perfect.
Perfect.
Okay. So just let me know when to start.
Okay. Okay, I think we can start. Today we are very happy to have Avia from Salmon Center in Stony Brook. She will tell us about renormalization group flows on line defect. Avia, please.
So hello, everyone. First, I would like to thank the organizers for the opportunity to speak and present these works. This talk will be based on two papers. One, this paper. It's a work that was done together with Gabriel Cuomo and Zohar Komargodsky, and on a work that is currently in progress together with Gabriel Cuomo, Zohar Komargodsky, and Mark Mazei, all from the Simon Center. So this is the outline of my talk. First, I'm going to give an introduction into the subject of line defects in conformal field theories. I will describe the motivation and some general arguments about line defects in CFTs. Then the second part of the talk will be the main part of it. It's about renormalization group flow on line defects. I will present the main idea, discuss defect RG flows, introduce spurion analysis, define a G function and a defect entropy, and then derive a gradient formula for the defect entropy. Then the third part of the talk, I will give a few examples. I will give the example of a Wilson RG flow in n equals 4 super Young mills, an example of a single scalar field, and models of impurities with large isospin. And then we conclude. Okay, so first introduction to the subject of line defects in conformal field theories. So first, let me explain the motivation. So in this talk, we will be interested in studying renormalization group flow properties of systems that are one-dimensional defects that are put inside a bulk that is a d-dimensional CFT. Now, such a setting is relevant for various physical systems. There are many examples. So, for example, in 2D, there are lattice systems with impurities, such as Kondo problems. In 3D, there are symmetry defects. For example, one can take a 3D Ising model and add a Z2 twist line operator. This was done in these two papers. Here from Monte Carlo perspective, and here from numerical bootstrap and epsilon expansion. Other monodromy defects can be found in here. In 4 dimensions, examples include Wilson or toothed lines in gauge theories, including applications to supersymmetric systems, such as Wilson lines in n equals 4. So there are many, many references. Here I put these two because they are in particularly important for the examples that I will show next. And also there are models of magnetic impurities, that is, you take some conformal bulk and you add a magnetic impurity. Examples can be found here, and also I will show an example towards the end of the talk. So in this talk, as I said, we will focus on line defects, meaning one-dimensional defects inside a bulk that is a d-dimensional CFT, and we take the number of space-time dimensions of the bulk theory to be larger or equal to 2. And what we will see that the bulk, we will see that the bulk CFT puts non-trivial constraints on the renormalization group flow on such line defects. And we will also see that the flow on such line defects is consequently irreversible, and that a canonically decreasing entropy function exists. Now, in a way, this construction will generalize what is known as the G theorem to line defects in an arbitrary number of space-time dimensions. So first, some general arguments about line defects in conformal field theories, some general arguments that will be important for the rest of the talk. So we consider local reflection positive Euclidean CFTs in any number of space-time dimensions, d larger or equal to 2. And we add a line defect to it in a way that preserves the unitarity and locality of the theory. Now, a definition now. So when I say a DCFT, a defect conformal field theory, I refer to the fixed points, meaning by definition, a DCFT is such that it preserves, the defect preserves the conformal group. So for example, for the straight line, we wanted to preserve SL2R times SOD minus 1. And that's the definition of a defect conformal field theory. Now, an important comment on this context is the following. If we have a line defect in a defect conformal field theory, then it does not support a defect stress tensor. There is a nice discussion about that in a paper by Herzog and Huang from 2017. The reason is very simple, because for line defect, the defect stress tensor has only one component, and conformal invariance of the DCFT demands it to be traceless, and therefore line defects in DCFTs do not support a defect stress tensor. What that physically means is that at the fixed points, there is no possibility to localize energy on the line defect, and energy always ends up being smeared into the bulk. Now, one can show that the following word identity holds for DCFTs with line defects. So here, mu nu B is the bulk stress tensor. Di is the displacement operator. It parameterizes the breaking of translations in the directions that are normal to the defect. Ni nu is the basis of D minus 1 unit vectors that are normal to the defect, and delta D is just the delta function that is localized at the defect. Now, one can understand this word identity as simply arises from the breaking of translations in the direction that are normal to the defect, but one can also formally derive it using a background field approach, like where you vary the effective action with respect to metric and the embedding functions, and derive these identities and also other identities for general DCFTs. So examples of such formal derivations can be found in many references. For example, in a paper by McCavity and Osborne from '93, in a paper by Jensen and O'Bannon from 2015, and in the appendix of a paper that we recently sent together with Gabriel Como and Marc Mazei. So in this talk, we will be interested mostly on circular line defects. Circular line defects that are put inside a bulk that is just d-dimensional flat space. Now, naively, one can say that a defect on an infinite straight line is conformally equivalent to a circular defect. However, there is a subtlety that is associated with the infinite extent of the straight line. So let me explain what this subtlety is. So we can consider a straight line defect, D, and we define it to be extended in the this direction. So this is XD. And the other directions, XI are the directions that are normal to the defect. I and J run from 1 to D minus 1. They go transverse to the line. Now, we assume a maximal symmetry, meaning that the line defect conformal field theory should preserve the SL2R times SOD minus 1, meaning we want to have translations along the line. We want to have invariance to rotations of the remaining XIs. We want to have invariance of scaling symmetry and special conformal transformations. Now, using these symmetries, one can show that the one-point functions of the stress tensor are given by these expressions. Here, R squared is XI squared, meaning that R stands for the distance from the line operator. And HD is a coefficient that depends on the content of the theory, meaning it's a physical characteristic of the DCFT. Now, these expressions were first derived in a paper by Kapustin from 2006. And this HD coefficient that is a physical characteristic of the specific DCFT, it was calculated in various examples. For example, in many supersymmetric systems, in all these references, one can find examples of calculations of this HD coefficient. So now we want to look at the following quantity. We want to consider the expectation value of the SL2R charges. So these are just obtained simply by integrating the stress tensor contracted with the appropriate components of the killing vectors associated with the SL2R and integrated around a surface that wraps the operator. Now, if we would, for example, when we have point-like operators, so we usually just wrap them with some topological surface like a sphere in order to get the charge. Here, our operator is a line operator, and the best analog for that would be to wrap the line operator with an infinite cylinder. So now, conformal invariance of the DCFT, it implies the vanishing of the SL2R charges, also the SOD-1 charges, that wraps the defect, even in cases where the surface intersects the defect. Now, for non-conformal defects, what happens is that these charges vanish whenever the surface wraps the defect and do not intersect it. But when the defect is conformal, then these charges should vanish even in cases where the surface intersects the defect. One quick way to see that is you can imagine here cutting this line with wrapping it with a small box that cuts the line. And then you can calculate these charges and use this word identity. And the normal components don't contribute anything, they just vanish automatically. So you end up integrating over nothing, and therefore the charges vanish. Now, so for conformal defects, the charges must vanish even in cases where the surfaces intersect the defect, by definition of the conformal field theory. However, it turns out that for the straight line, there is a problem, even if we just consider surfaces that wrap the defect and do not intersect it, like the infinite cylinder. So in this case, if we take the dilatation and special conformal kinning vectors of the SL2R, then we get that for the straight line, we get a double divergence. We get this term, which goes like the length of the cylinder times 1 over epsilon, where epsilon stands for the distance from the line operator. This phenomena, this double divergence, it was first observed in the paper by Kapustin. Now, this divergence is in sharp contrast with the expected charge conservation and the conformal invariance of the bulk, because these charges must vanish, and here for the infinite cylinder, they don't. Now, this problem with the straight line is probably related to the disagreement that exists in the literature between the expectation values of the circular and the linear Maldacena-Wilson loops in n equals 4 super Young Mills. So, for example, in these papers, the authors calculated the expectation value of the circular loop and the straight line Maldacena-Wilson loop in n equals 4, and they found disagreements. They got different results. So this issue is probably related to that phenomena. However, no issues of this sort arise for circular defects. So we consider a circular defect of radius r that is centered around the origin of the x1, x2 plane, and the other coordinates sit at 0 for the defect. And in this geometry, we can again wrap our line operator with some surface that wraps the defect like a torus, like in the figure. And then we can calculate the expectation values of the SL2R charges. And we find that for all of them, for all of the three conformal killing vectors, the charges automatically vanish when we take the circular geometry. And this means that circular defects truly preserve the SL2R charges, and therefore they will be a good settings for our purposes to come next. So we will focus on circular defects from now on, circular defects that are put inside a bulk that is just flat space, d-dimensional CFT. So now
can I ask a question? Here in the circular case, what happened for the transverse part of symmetry?
The SOD -1, you mean?
Yes.
The charges vanish too.
You mean the symmetry is still there in this case?
Yeah, what happens is you had before, okay, for the straight line, you have SL2R times SOD -1. And for the circular line, you also get some SL2R times some SOD -1. And the charges vanish for all the symmetries for the circular geometry.
Okay, thank you.
Okay, so now I move on to the second part of the talk, which is about renormalization group flow on line defects. So first, I will just say the main idea and the main result, and then I will explain how we derived it. So the main idea is that by surrounding the line defects with conformal charges, we get non-trivial identifications when the defect is non-conformal. And these identifications can be expressed in terms of constraints on the dilaton that is living on the line defect. And our main result is that we show that these constraints translate into a monotonically decreasing entropy function. So a defect RG flow. A defect RG flow can be triggered by perturbing the DCFT with one or more relevant defect operators. So we consider a defect operator O with some scaling dimensions delta O smaller than 1. And we change our action by this term, where here M0 is the mass scale that is associated with the flow. And int D stands for integration along the defect. Sigma is the line coordinate. So now we added an RG flow, and this means that conformal invariance is now explicitly broken by the existence of this mass scale M0. And it is.
I have a question. So you said before that the defect preserves the unitarity. I mean, is this conformal dimension of this defect operator satisfy the unitary bound of?
For unitarity, for theories that are reflection positivity, we have delta O larger than 0.
Okay.
Okay. We will need the unitarity to show that the defect, the sign in the defect function is manifestly negative. Okay. So now, once we turn on a mass scale and we have a flow, then conformal invariance is now explicitly broken by the mass scale to just translations along the line, as long as these perturbations are homogeneous. So now, because we added an RG flow, this means that the word identities get modified. So for the bulk, we assume locality of the bulk CFT, and this means that the bulk stress tensor is conserved and traceless, at least away from the line. However, by turning on a defect RG flow, it is no longer true to say that we cannot store energy on the line defect. By turning on an RG flow, energy is stored on the line defect, and therefore a defect stress tensor exists. So we denote it by TD, and the word identity from before gets modified by the addition of this new term, where here a dot stands for derivative with respect to the line coordinate sigma, and x nu dot is a vector that is just tangent to the defect, meaning x mu is the embedding function. It parameterizes the location of the defect. And this equation, what it physically means is just it expresses the energy balance between the bulk and the defect. Now, so now we added an RG flow, and this means that the SL2R charges are no longer conserved. And what this means is that if the charges are now integrated over surfaces that intersect the defect, then it is no longer true to say that they are invariant under small deformations. So, however, and this is important, these charges will still continue to vanish whenever the surface that wraps the defect wraps it and do not intersect it. They must still vanish for every surface that wraps the defect and do not intersect it. And the reason is because for charges that wrap the defect and do not intersect it, they don't see what's going on the line defect, meaning they remain invariant under small deformations. So one way to understand that is the following. You can imagine the torus wrapping the defect as the difference between two SD-1 spheres, one that is sitting inside the defect and one that is sitting outside the defect. And for the one sitting inside, then there is nothing in there. It gives 0. And for the one sitting outside, then you can take it to infinity, where it annihilates the vacuum. So you also get 0. So these charges vanish whenever the surfaces do not intersect the defect. So now we are ready to introduce a dilaton. We use what is called spurion analysis in the literature. So we do that by promoting our renormalization group scale M0 to be a function of the line coordinate sigma. So we parameterize it like that. We choose M of sigma to be M0 times e to the phi of sigma, where phi of sigma is a dimensionless background field that we will call the dilaton. It has nothing to do with the string theory dilaton. It's just a tool, like a gadget, that we will use in order to remember the RG flow. And it acts as a source for the theory. And to linear order, one can calculate how the partition function changes once we change a little bit the dilaton. So it just couples to the defect stress tensor. Now, because we now broke the translations along the line by having this mass scale that depends on the line coordinate, then we actually broke the SL2R completely. And then again, the worded entity gets modified. And one can calculate how it is modified. And it is modified by this amount, by this new term here. Now we can use this equation in order to derive some non-trivial identities that will relate different theories with different values of the sources, phi of sigma. So, so as I said, by having a position-dependent mass scale, we broke the SL2R symmetry completely. But what we gain by introducing this dilaton is that the SL2R symmetry will allow us to relate different theories with different values of phi of sigma, instead of directly putting constraints on a given theory. So this identity, the vanishing of the charges for surfaces that wrap the defect and do not intersect it, it holds even if we broke the translation invariance on the defect. And what we do below, we will derive the consequences of this condition, this equation, together with this worded entity. Okay. So if we use a Gauss law and the worded entity, this one, then what we get is this expression, where here zeta d is the projection of the killing vectors associated with the SL2R on the circular defect. Now we get this expression, and now due to the linear coupling between the dilaton and the stress tensor, this coupling, then we can interpret this relation as simply the equivalence between theories with some phi and theories with phi modified by this amount, where alpha is some infinitesimal parameter. And so this equivalence holds for every alpha, and that is infinitesimal, and for any of the three conformal killing vectors of the SL2R. Now, this equivalence.
Sorry, Avia, can you explain the last equation? Yes, in this phi equivalent to phi plus alpha. Where did you derive this one?
So, so what you do, you expand the partition function.
Yes.
And you demand that having a partition function with some phi is the same as having a partition function with this phi. Oh, sorry, you mean?
Yeah, that's the consequence, but how did you get this?
How do I get this?
Yes.
Oh, it's because I see that the integration here must vanish. And you know that the dilaton couples linearly to the stress tensor. Okay, so it couples like this, and if I go back, then here also we have a stress tensor. So the dilaton must be shifted by this amount. And the reason that it's infinitesimal, it's because I use an expansion of the partition function in here.
I see, but that's only the linear order.
That's well, that's to the leading order, but I mean, to the linear order, it's correct, and we will use an expansion of the fields such that we can plug this relation, and it makes sense. Okay, so okay, so okay, I already said the consequences. But we can get identities once we expand the partition function around, so we expand it around phi equals 0. Phi equals 0 is just the state that has translations invariance over the circular defect. And one of these identities is this identity. And this will give us new constraints that are interesting. And this identity must hold crucially for any phi of sigma and for any of the three conformal killing vectors. So now.
So phi is arbitrary field, right?
Yeah, that depends only on the line coordinate.
But then if I plug in different phi, then I get this constraint too. You basically infinite constraint.
Like, okay, you must okay, on both sides of it, right? You can get depending on which phi of sigma you're putting, you will get some constraints on the correlation functions. We picked one that will be in particularly useful for us. You may get constraints, you may get something that holds trivially.
Yeah, but I'm a little confused. So the 1-point function of TD and 2-point function of TD, these are all independent.
These are evaluated in 0 phi, yes.
Independent of phi, right? So
what?
Independent of phi, this 1-point function and 2-point function of TD.
The 1-point function are at phi equals 0. Yeah, because I expanded the partition function to get this equivalence. I expanded it to like around 0 source.
Yeah, so that means that if I give for given theory, for given deformation, or this TD and the TD are fixed, right? Are determined. I mean. Then how could this determined function satisfy infinite constraints?
These TD are evaluated at 0 source. They are invariant for translations along the circular line.
Yes.
They are evaluated over a 0 source because you expand the partition function around a 0 source. Okay.
Yeah, yes, basically independent of the profile of phi function, right?
Yeah, I can pick any phi here. It's an expansion in the fields. You expand around phi equals 0. I use this, but with phi equals 0 and some phi here. And then I get the equivalence. And the equivalence will therefore give me here functions that are evaluated at phi equals 0. It's important for me to have it evaluated on phi equals 0 because at the end I want to deduce something about the state which has translational invariance on the line defect. Okay.
Okay.
So crucially, this identity must hold for any phi of sigma and for any of the 3 conformal killing vectors zeta d. So now it's a good time to specify a coordinate system. We use what is called a cylindrical coordinate system. So we pick x1 to be our cosine phi, and we pick x2 to be our sine phi, and we set sigma to be r times phi. And now we can calculate the projection of the 3 conformal killing vectors associated with the SL2R. This is the result. This one is just simply for the translations along the line. Now, if I take this identity and I pick the 3rd conformal killing vector, then I don't get anything interesting. But for the other 2 conformal killing vectors, we do get non-trivial identifications. So for example, if we pick the first one, the 1st conformal killing vector, and we choose phi to be cosine phi, then we get this equation. Now this equation relates, and from now on, I omit the subscript of phi equals 0 in correlation functions. So this equation relates the integral over a 1-point function of the defect stress tensor to a double integral over a 2-point function of the defect stress tensor times the cosine of the relative angle. And this identity will be very useful in providing a gradient formula for the defect RG flow, as we will soon see.
So if I take a capital phi, like a cosine square function, some other type, so you basically get other constraints.
Yeah, if you pick different dilaton, different value of the dilaton, you get some other constraint. Maybe it's linearly dependent, maybe it's not. Depends what you pick. This was in particularly important for what we needed next, and we can do it for any phi. So in particular, we can do it for this particular phi.
Okay.
Okay, I guess I have another related question. So is it possible to use this equality for any big phi to fix the 2-point function of t in terms of the 1-point function of t?
Well, you have this cosine, but
right. If you pick all possible big phi's and you write infinitely many equalities, is it enough to fix the 2-point function in terms of the left?
Is it enough? I'm not sure I understood your question. Can you explain again?
So basically you have infinitely many integral equations relating to functions.
Right.
So I'm asking, the left is about the 1-point function and the right is about the 2-point function. The 2 integrals.
Yeah.
And the question would be, is this infinitely many equations enough to fix the 2-point functions in terms of the 1-point?
In terms of the 1-point.
Or how powerful is this equation to relate the 1-point and the 2-point functions?
I guess you can always.
It's very powerful. It seems it's a very powerful equation.
Yeah, it's a powerful equation because you can always replace the integral over the 1-point function evaluated over a 0 source with this integral, like of the 2-point function also evaluated on a 0 source times this cosine of the relative angle. I mean, so that's an important identification. I would say for sure it determines the integral over TD.
I see. Okay, thank you.
Okay.
Sorry, I have a question. I'm actually a bit confused. Are you doing conformal perturbation theory here, or this equation is the
No.
non-perturbative result?
No. It's this expansion. It's expansion in order by order in the field, but it's
Okay.
not. It's not a perturbative.
I see.
It's not perturbation theory. It's just that you get infinitely many equations, and they must all be satisfied order by order in the field expansion. And we just took the first orders and checked what we get from there. If you continue and derive higher and higher orders, you get new identities. Maybe some of them are useful, maybe not. But we just needed this one.
Okay. So, okay, I see. So that means, I mean, the deformation is not necessarily to be small, right? You can be.
It's like an infinitesimal expansion. You should make the expansion in take enough terms so that it's consistent. I mean, but you can look at higher orders and but as long as you take this, as long as it's consistent, as long as like you take the proper order.
I see. Okay.
You do get infinitely many identities, but here we needed just this one. This one, it's the first, not the first, the second order. It's like, okay. Okay. Should I continue? Okay. So,
sure.
Okay. So now I will define just one step, one more comment before I will define the G function and the defect entropy. So the discussion so far has focused on line defects. There are circular lines inside a bulk that is just flat space, but all the considerations will apply equally well on all conformally equivalent manifolds. For example, we can take, we can speak about the sphere SD, with the line defect spanning around a maximal circle. We can also take the cylinder R times SD minus 1 with the line defect sitting on the equator of an SD minus 1 sphere at some fixed value of Euclidean time. So we can use any of these geometries, and we can use any of these geometries in order to define a defect G function. So the defect G function is defined by the partition function in the presence of the defect, normalized by the partition function without the defect. So here, this refers to the whole theory with the defect, and this refers to the theory without the defect defined over the same regime. And then a natural question to ask is, what can this G be a function of? Well, in general, the defect contribution G, it can depend only on the dimensionless product, which is M0R. So G is a function of M0R. Now, the next natural question to ask is, to what extent is this G well defined? Well, in dimensions larger than 2, then it is defined up to a cosmological constant counter term, because log G can be shifted by the addition of a cosmological constant counter term of this form. So it's just M0R with some arbitrary coefficient. And in dimensions bigger than 2, no other ambiguities exist. We will discuss the two-dimensional case really soon, but already this cosmological constant possible counter term, already this motivates us to define the following quantity S that we will call it the defect entropy. So it is defined as simply 1 minus R partial R of log G. And by its definition, it is scheme independent and it is free of any ambiguities, at least in dimensions larger than 2. I will discuss the two-dimensional case on the next slide. Now, at the fixed points, then this S is just a pure number that is equal to the universal part of log G, which is scheme independent, and it depends on the intrinsic properties of the system. We will call these fixed point values as of G as GUV and GIR. Now, let me comment regarding the two-dimensional case. So in 2 dimensions, we can also have this counter term, where K is the extrinsic curvature. Now, such a term vanishes for a maximal circle on S2 and also for the cylinder R times S1. But also in flat space, we can use CPT. CPT invariance implies that the coefficient of this counter term should be purely imaginary. And therefore, the definition of the defect entropy S, it makes sense also in 2 dimensions, provided that we focus on the real part of the defect entropy. Now, an interesting question to ask is the following. How does this G evolve? Meaning, how does this G interpolate between the UV entropy of the defect and the IR entropy of the defect? And what we will see in a minute is that the defect entropy S decreases monotonically under a defect RG flow, which implies that GUV is always larger or equal to GIR. Now, we need just one more technical step to derive this. So for a constant background field, S it depends on this, on M0 RE to the pi. And then we can use Fourier analysis to basically relate the gradient of the defect entropy to an integral over the 1-point function of the stress tensor and the integral over a 2-point function. Now, this identity, it may not seem very useful at first sight because it is not sign definite, nor it is free of divergences, but we can use the identity from before, the one that I said it would be useful, this one. We can use it in order to replace the integral over the 1-point function with this expression in the identity here. And if we do that, then we get this identity. Now in here, the right-hand side is free of any divergences and ambiguities due to the double zero in the 1 minus cosine of the relative angle. And it is manifestly negative in a theory which has a reflection positivity. And therefore, this means that the defect entropy S monotonically decreases under a defect RG flow, which implies that the UV and the IR DCFTs must satisfy GUV larger or equal to GIR. So this is the gradient formula. Now, I would like to just tell you a little bit about what was done in the literature before this analysis that I've just shown. So in 2 dimensions, the inequality GUV larger or equal to GIR, it was originally conjectured to hold for boundaries, boundary CFTs in 2 dimensions in a paper by Affleck and Ludwig from 91. Now, in 2D, in the regime where the defect RG can be described in terms of finitely many couplings and beta functions, then a gradient formula similar to the above was proposed in the context of string field theory in these papers. Then Friedan and Konechny established in 2004. And a bit later, an alternative proof for the 2-dimensional claim was given in a paper by Casini, Salazar Landea, and Toroba from 2016, and they used methods of quantum information. Now, this inequality, also let me mention that this inequality GUV larger or equal to GIR, it was recently conjectured to hold for arbitrary dimensions in a paper by Kobayashi and collaborators. And we can say that our work provides an extension of these these results in 2D to a line defect in an arbitrary number of space-time dimensions. One more comment I want to say regarding the proof of Cassini and collaborators using methods of quantum information. They use the fact that at the fixed point, the defect entropy that I defined here and the defect contribution to the entanglement entropy, they coincide in 2D. However, in general, this relation is not true. The defect entanglement entropy for higher dimensions is different in general than the defect entropy that I defined. And here we have seen that the quantity that is monotonically decreasing under a defect RG flow is the defect entropy. And this makes it challenging and interesting to try to extend this proof to be written in terms of quantum information language. So this is an open problem, whether there is a quantum information interpretation of the monotonicity function for higher dimensions as well and line defects. Okay, so now I will present some examples.
Yeah, is this 1 minus R partial R unique formula, or there are some other alternatives? Could be. Is it unique?
Well, you need a quantity that will be scheme independent, and at least in all dimensions larger than 2, this is enough to get the quantity that is scheme independent. I mean, log G is not free of ambiguities, but this 1 minus R partial R is free, and because it is it's scheme independent and it's free from ambiguities, this makes it a good candidate in the first place to monotonicity, and it works. So it's a right candidate.
Okay.
Sorry, I have a question. So is this formula somehow related to like the beta function of the coupling that triggers the RG flow?
Yeah, if you have like a perturbative flow, then yes, because what usually happens for perturbative expansion, then this TD is like a beta function times the operator, and yeah, you will see also in the examples that I will just show that you get here contributions, right, proportional to beta function squared. But this formula is non-perturbative. You can use it also in a non-perturbative regime. Okay, so now I will show some examples. So in 2D, there are plenty of examples that show that GUV is larger or equal to GIR. So we wanted to verify this formula in some concrete examples in higher dimensions. We did that in conformal perturbation theory. And in 3 examples that I will show, first, RG flow from standard Wilson loop to the supersymmetric one in n equals 4, the flow that was proposed in the paper by Polchinski and Sally, at weak Tooth coupling. A model consists of a single scalar field and models of impurities with large isospin. So the first example that I will show is a Wilson RG flow in n equals 4. So we consider a defect RG flow from the ordinary Wilson loop to the 1/2 BPS Wilson Mandelsena loop in n equals 4 in 4 dimensions in the planar limit. This model was studied extensively in the paper by Baccaria, Guillaume, and Zeitlin from 2018. And we used many of their results in order to verify the gradient formula in this case. So we consider a single parameter family of Wilson loop operators in the fundamental representation. The operators are given by this expression, where here theta m squared is 1, and zeta is the coefficient that sits in front of the scalar coupling. M runs from 1 to 6, and we focus on circular contours. Now, this theory admits a UV fixed point at zeta equals 0, that's the Wilson loop, and an IR stable fixed point at zeta equals 1, that's the Wilson-Mandelsena loop. This was discovered in the paper by Polchinski and Sally. This flow was proposed. Now, generically, the expectation values of the Wilson loop operators are some functional that depends on the Tooth coupling lambda that does not flow, and on the zeta parameter, which does flow, and it is a function of M0R. It has a beta function. So in the small Tooth coupling regime, Polchinski and Sally calculated the beta function, and it is given by this result. Now, in the paper by Baccaria and collaborators, it was found that the expectation values of the Wilson loop operators are given in the weak Tooth coupling regime by this expression. Note already we can see from this expression that GUV is larger than GIR. And also notice that these results, despite being perturbative in lambda, they are exact through the flow, meaning from this expression holds from zeta equals 0 to zeta equals 1. Now, already we see that GUV is larger than GIR, but we can do better than that. We can compute the gradient of the defect entropy using the result. And we get this expression, which is manifestly negative, and therefore the defect entropy S monotonically decreases as expected. We can still do a bit better than that. So we can use the result from their paper in order to extract the 2-point function of the defect stress tensor. It is given by this expression. And if we plug this expression on the right-hand side of the gradient formula and integrate with 1 minus cosine of the relative angle, then we get a complete match between the right-hand side of the gradient formula and this result. So we verified explicitly the gradient formula in this example. The second example that I will show is a single scalar field. So we consider a single free scalar field, free at the bulk. Bulk is just a free theory with a single scalar field. And we add a line defect to it. And the line defect is linear in the field. That's the line defect. M0 is the mass scale, lambda is the coupling. Now, this theory one can simply solve, and it's just equivalent to having a free theory with no defect at all that sits on top of a classical background. And one can take this model and solve it and calculate and show that the defect entropy is given by this expression, where CD is a coefficient that depends on the number of space-time dimensions only. We can plot it for d smaller or equal to 4. This is the plot, and you can see that it is always negative. And what that means is that the defect entropy S goes to minus infinity in the deep infrared when R goes to infinity. Now, also one can verify explicitly, and these results also are in agreement with the gradient formula.
Now, how this little s is entropy, how it can be negative?
How I can derive this little s?
How it can be negative. This little s is entropy.
How it can be negative? Well, at the fixed points, s is log g. G is always positive in theory, which has reflection positivity, but it can be smaller than 1. And when it's smaller than 1, then the defect entropy is negative. Okay. G cannot be negative, but S can. Okay, so the third example that I will show is perhaps the most interesting one. So now we take 3 scalar fields. So phi A runs from 1 to 3 scalar fields, and we take the bulk theory to be just a free theory. And we add a line defect to it, which is just an impurity in the spin S representation of the bulk global O3 symmetry. So we add this line operator, where gamma is the coupling and phi is phi A LA, where LA are the 3 matrices that are in the 2S plus 1 representation of the global SU2 algebra. Now, for values of spin impurity of order 1, then one can study this model perturbatively in epsilon expansion around 4 dimensions. So this was done in several papers, for example, in these two, and they calculated the beta function associated with this gamma, and it is given by this expression. It has one fixed point. And now this expansion, when we take S to be larger and larger, the perturbative expansion will break at some point because you can understand it intuitively by thinking that the factors that multiply Feynman diagrams are factors of S, positive powers of S, and at some point you can no longer neglect higher loops. Now, naively, if one do a naive analysis, meaning from this expression you realize that epsilon goes like gamma squared, and from here you read that whenever you have one gamma, you also have one matrix, meaning one S, then one can naively think that the perturbative expansion should break down once S is of order epsilon to the power of -1/2. But apparently it's not the case. And the perturbative expansion breaks down once S is of order epsilon to the -1 and not epsilon to the -1/2. Now, to understand this in terms of diagrams, it's pretty difficult, but one can understand it from just a different approach that I will show on the next slide. So as I said, for larger and larger S, the perturbative expansion breaks down. And we need a different approach to attack large S cases. So what we found was that we can use a semi-classical approach that recasts the expansion in a double scaling limit. Double scaling limit that is defined such that S goes to infinity and epsilon goes to 0, such that the multiplicity of epsilon times S remains fixed. And this is interestingly very similar to the results in a paper by Badel, Cuomo, Monin, and Rotazzi from 2019, where they studied O2 model in near 4 dimensions with no defect at all, just large charge analysis. And they calculated the scaling dimensions associated with heavy operators. And they also found a very similar, they found a double scaling limit that this double scaling limit that I will just show, it acts very similar to what went on in their paper. So one can show that this model can be written by the following expression. So here I introduced a Z, which is a bosonic bispinor. It has 2 complex components, and it must satisfy this constraint in order for the 2 models to be equivalent. Now, the advantage of having this approach is that we can do, after we do a rescaling of the field, we take phi a to be square root of S times phi a, and we take Z to be square root of S times Z, then one can identify S to the power of -1, like plays a role of H bar, meaning that we can do a systematic expansion in negative powers of S. Now, this model can be therefore analyzed semi-classically in the following double scaling limit that we take gamma to 0, S to infinity, such that gamma squared S is fixed. And if we do that, we can write the G function normalized by the G function in the UV. We can write it in this expansion. So you can see that the first term has a positive power of S, S to the power of 1. The second term has S to the power of 0. And the third term goes S to the -1 and so on, meaning expansion in negative powers of S. And these functions, these F functions, F-1, F0, etc., they are regular functions that depend only on the parameter that we kept fixed, the gamma squared S, the double scaling parameter, and the number of space-time dimensions T. Now one can calculate these functions order by order in a semi-classical expansion and verify the agreement with the gradient formula. Interestingly, we can also use the semi-classical calculation to compute the beta function of the theory. So we did that, and this is the result. I will say why it's interesting in a minute. Here I just defined alpha to be gamma squared s for convenience, and this is the beta function. Now, if we expand this expression in small coupling, small coupling, then we go back to the single fixed point that existed in the perturbative expansion in the papers by Sachdev and other collaborators too. Now, in general, the fixed point in the double scaling limit is given by this expression once we set to 0 the beta function. And okay, if we are exactly in 4 dimensions, epsilon s is 0, and then we have just one trivial stable fixed point at alpha equals 0. But if we look at the regime where epsilon s is larger than 0 but smaller than 1 over pi, then interestingly there are 2 solutions to the beta function equals 0 equation. One solution is given by this that we called alpha 1, and you can expand in small epsilon s because epsilon s is smaller than 1. And to the leading order, it is given by this. This is just the same perturbative result that appeared in the papers by Sachdev and collaborators. However, there is now a new fixed point, a new solution to the beta function equation. And it is given by, this expression that we call alpha 2. And if you expand it, you see that it goes like 2 over pi squared epsilon s, meaning that this new fixed point is a strong coupling. Now, okay, only the fixed point with alpha equals alpha 1 is stable, and that's for this regime. Now, if we look at the point where epsilon s is 1 over pi, then the 2 solutions coincide. And for epsilon s larger than 1 over pi, then there are no solutions. So one can calculate, we calculated using a semi-classical expansion. You can calculate the G function, and we get this expression. So you can see the first time is the leading order. This is the next leading order, plus there are order 1 over s corrections. And if we plot log of G2 over G1, then you can see that it is always positive, where log G2 refers to log G in the fixed point value of alpha equals alpha 2, and log G1 refers to with the fixed point of alpha 1, the same, but with the fixed point of alpha 1. And you can see that the difference is always positive as expected from the gradient formula. Okay. So now let me summarize and conclude. So what do we
just confirm? So in those examples, when you see agree with gradient formula, that you mean you refer to the gradient formula with the capital phi equals to cosine little phi?
No,
which one?
This one. You can calculate the entropy by the change in the partition function by evaluating the partition function, and you can calculate the stress tensor and plug and see, and this is what we did to verify.
Yeah, this was derived from this capital phi take as a cosine, right?
Yeah. But when we derived this. Yeah, of course, this was derived using the previous identities. Yes.
Okay.
Okay. So let me conclude. So we found that the bulk CFT puts non-trivial constraints on the RG flow on offline defects. And we show that these constraints translate into a monotonically decreasing entropy function for the defect given by this expression, and that this gradient formula is satisfied. And we've checked this in various applications. We've demonstrated it in various applications. Now, there are many open questions left for the future. One obvious question is, what about higher dimensional defects? Like, can one extend similar proofs for the cases that are not yet solved in the literature? So in this context, I will mention that for two-dimensional defects that are put inside bulk that is in 3 dimensions or higher, this case was studied in the paper by Jensen and O'Bannon from 2015, where they proved a defect B theorem, meaning that the coefficient of the Euler density in the defect Weil anomaly acts as a monotonic function and decreases through the RG flow. Now, similarly, for 4-dimensional defects in a bulk that is in dimensions larger or equal to 5, this case was analyzed recently in a paper by Wang from 2021. He proved the defect A theorem, again, for the coefficient in the Euler density of the defect Weil anomaly. Now, there is the open question that I already mentioned about whether there is an interpretation of this formula in terms of quantum information theory. Another interesting question is the following. If we have some CFT in the bulk, are there any restrictions on the universal part of log G at the fixed points? Meaning we know that the defect entropy S decreases, and the question is whether there is a bound on this on the lowest value, given some assumptions about the spectrum of the bulk. So some progress in that direction, in this direction, was made in a paper by Friedan Konechny and Schmidt-Collinet from 2012. They studied in the context of 2-dimensional boundary CFTs, and they made some assumptions about the spectrum of the bulk operators in order to derive bounds on the defect entropy. Now, so it will be interesting to try to extend, get bounds in higher dimensions as well. Also, in this context, the following question is interesting. The question is the possibility to have an entropy that goes to -infinity is attached to the existence of a moduli space of vacua, like we thought that S goes to -infinity for the free scalar field, for the scalar field that was free in the bulk. So it is a question whether it is possible to have S go to -infinity whenever or only when maybe there is a moduli space of vacua. Okay, thank you very much for listening.
Thank you. Thank you for the very nice talk. So in the last slides, you mentioned the lower bound. So at least in 2D, there could be a 0 boundary entropy. Do you seek for some positive lower bound or just general low bound? So of course, it's a low bound under some assumption about the bulk spectrum, because in general, like we saw in the free scalar, it can go to -infinity. So, for example, in this paper, what they did is they made assumption about the dimension of the lowest. I mean, about the dimension of the most relevant operator of the bulk, that it is bigger than something, than C-1 over some factor, where C is the central charge, and then they got that that it's like it's not negative for these 2D boundaries. But they made some assumptions about the spectrum of the bulk theory. They made this assumption and another assumption about the central charge. I see. Another question is, if I just put this your argument in 3D, think about F theorem, can this provide alternative proof of F theorem? Because I can view this entanglement entropy twist defect as also a one-dimensional defect. I didn't hear your last line. I'm just curious if I use this argument in 3D, can I prove F theorem?
You mean, what do you mean by F theorem? For
Because I can consider the entanglement defect or twist defect as a one-dimensional defect. If your argument also applies there, then I can.
Yeah. Okay. So this formula, it holds for any one-dimensional defect under the assumptions that we made, like locality and reflection positivity to get that the coefficient is negative, and invariance for translations along the defect. So of course it will hold in three-dimensional theories as well for one-dimensional defects. Yes. I mean, under the assumptions that we made.
I see, thank you. Are there other questions? Both online and offline. Are there more questions? I saw, Avia, can you see the chat? Because I saw a question.
I can stop the sharing and then I will be able to see the chat. Do you have counterexamples if you relax one of the assumptions? Well, I mean, okay, so of course, some of the results will be ruined unless we have these assumptions. Like if you let go of reflection positivity, then you will not be able to say that it's monotonically decreases under a defect RT flow because the sign is not manifestly negative. Probably this equation will still be correct, but the conclusion will not be correct that the entropy decreases monotonically. So, so that's one example. Another example is that we did assume translation invariance along the line. The formula is evaluated at zero source. I don't know what will happen. We don't know what will happen. I don't know if we let go of this assumption. Probably this breaks down. I mean, for sure, the derivation will break down if there is no invariance for translation invariance, because to satisfy these constraints, we needed that. Yeah. Yeah, it should be easy to construct counterexamples, but
are there more questions from the students? So you mentioned some quantum information interpretation of your defect entropy. Why you expect that? Why do you expect there should be some?
Oh, some interpretation at all?
Yes.
Well, for the 2D claim, there was an interpretation, and also in regular QFT is like with no defects. So for example, in 3D, monotonicity F theorem was proven using methods of quantum information. So it's just interesting to know. Maybe there is and maybe there isn't an interpretation. I don't know.
I see. Thank you. Yeah, I saw Zohar is answering some for previous questions.
Yeah. So somebody.
Yeah, actually, I'm still slightly confused. So see, for the first example you raised, the Wilson loop,
Mm-hmm.
if I try to change the capital phi to another function of little phi, say cosine or sine, some other types, can you still confirm the using Wilson loop as an example to check that
So
like
okay,
another grading formula? Yeah.
so let me share it again. So the formula that we compared in the first example is this is the gradient of the defect entropy. We got it just by using Kalan-Zimanzik equation and taking the expectation value of the Wilson loop operators from the paper by Baccaria and collaborators. And this must be matched with an integral over this times 1 minus cosine of the relative angle, meaning we explicitly verified this formula. This is the gradient formula, meaning that the gradient of the defect entropy is always given by this integral of the 2-point function of the stress tensor times 1 minus cosine of the relative angle.
Yeah, but okay. My question was, I'm curious that if I plug in another capital phi function, so you basically get another constraint or maybe another gradient formula. Are these still true, or can you check that? Basically, you can check if you have examples.
If you put a different, if you choose here a different capital phi, do you get other gradient formulas? Well, but okay, what you want to achieve at the end is something that is free of divergences and counter terms. And this 1 minus cosine of the relative angle is very important because it makes it free of divergences and ambiguities because of the 1 minus cosine phi. So if you take this 2-point function at points that coincide when phi 1 goes to phi 2, then in general the 2-point function of the stress tensor can be defined up to contact terms. However, this 1 minus cosine of the relative angle, because if you expand it around like the point of when phi 1 goes to phi 2, then it is like phi 1 minus phi 2 squared. This is very important in order to get something that is free of any divergences and ambiguities. I mean, you want to work with something that is free of divergences and ambiguities. And that's the reason why this specific choice was extremely useful, this choice of here, because it enabled to write down the gradient in terms of something that is free of any ambiguities and divergences that may in general appear in a 2-point function of stress tensor.
Okay, thank you. There's one more question in the chat.
How about the residual entropy? What is the residual entropy? I don't understand the question. Sorry, I still don't understand the question.
Maybe you can speak. Who is that? Is
Oh, I major in the spin ice. The spin ice has a property. The entropy at this okay. Entropy. I research the ice and the spin ice, a magnetic material. I see your PowerPoint. It's PowerPoint start about the entropy. So I want to know yours.
Here it's the defect entropy.
Defect.
The defect, yeah, it's the defect entropy. That's the definition.
Oh my God, I don't. Oh, I see the entropy. So I want just be interested in your theories about the entropy. How can it can be used to analysis the residual entropy?
I don't know what is residual entropy, so I don't know how this can be used to analyze residual entropy.
Oh no, yes.
Maybe someone else.
Oh, sorry.
are there other questions? Comments? If not, let's thank Avia for the very nice talk again.
Thank you.
Thank you. Thank you, Avia.
Thank you very much.
Thank you very much for listening.
So are you in Stony Brook right now?
Yeah.
Okay.
Yeah, in my office.
Thank you. What was your last time to Tel Aviv?
Oh, a year.
About the widgets.
About a year ago. A year and 2 months ago.
Widget.
Thank you. Thank you
so much.
Thank you,
Thank you.
Zohar. Thank you, Avia. Bye-bye.
Bye-bye.
Bye. Bye.